We're going to talk now about virtualization. So this is based on a paper, A Comparison of Software and Hardware Techniques for x86 Virtualization. This was done by two authors at VMware. So they had lots of experience in writing a software virtualization. All right, so what is software So what's a virtual machine? A virtual machine it's a simulation of a computer. Okay, so a simulation of a computer running as an application on a host computer. So we basically got a computer here. So we have a computer. Within this computer, we have several applications. And the idea then is in one of these applications, we have this simulation of a computer. So this is a pseudo computer. And the goals we have for this simulation are that it be accurate. So it capture the real computer. It has high fidelity. That means in some cases actually accurate to the point of simulating bugs on the underlying computer. Also that it be isolated, so that nothing you're doing on this computer has any effect, for instance, on another application. And finally, that it be fast. Why would we want to do this? Well, one possibility is we want to run multiple simultaneous operating systems, for instance, Windows and Linux, right? Or if I boot Windows applications, I can do that with, there's a virtual machine called Parallels Desktop, so I can run a Windows inside of my Mac. I did that when I was doing development, for instance, of some Windows applications a few years ago. And so it was very helpful to be able to run my Windows while still having my traditional Mac for all my other applications. It's also nice for kernel development. So for example, your development of JOS, it's very handy to be able to run a virtual machine, which is QEMU, instead of actually having to boot up on real hardware. It is also handy sometimes to package applications. So you can basically take a virtual machine image that has an exact setup of everything that's installed that you want, the drivers installed, the applications installed, the kernel version, and so on, and then just use that to bring up. And in many cases, it can also improve resource utilization. So you can have multiple virtual machines running on a single piece of hardware, can sometimes get better utilization for that. How accurate do we have to be? Very accurate. We need, in some cases, to have bug-for-bug compatibility. Because what we may have is either applications or if you're running on a raw computer here, you could actually have an operating system on top of this. And so that operating system may be very dependent on the particulars of the hardware. We have to maintain isolation. So guests, that is whatever's running inside here. So we would have a guest OS here, and then guest apps. Guests can't break out. And a guest also, it has to be impossible for the guest to be able to tell the difference between a virtual machine and a real machine. It should look like a real computer. There are cases where some virtual machines compromise. They go ahead and actually modify the guest OS in order to make this run. That's usually done when the virtual machine manufacturer and the kernel manufacturer are the same manufacturer. So that's called para-virtualization. And it's interesting because by making just a few changes to this underlying guest OS, you can actually increase performance quite a bit. These are not a new idea. So in the 1960s, IBM used virtual machines to share their big iron. That was what's called their big machines. And in the 1970s, IBM actually specialized some of their CPUs for virtualization. In the 1990s, virtual machines came popular again. So VMware repopularized them for x86 hardware. And then in the 2000s, AMD and Intel actually have specialized CPUs now that aid in virtualization. We'll be talking about it in some more detail. So what do we get? We got, at the bottom level, our hardware. On top of the hardware, what do we have? An OS. So we've got an OS on top of the hardware. And then on top of that, we have applications. So for instance, we might have Vim, DB, and maybe, so that's our traditional single operating system approach. Now, how does this change? Well, when we're using virtual machines, here's what we'll do. So we still, of course, have our hardware on the bottom. And on top of the hardware, we may then have an operating system, which we'll call a virtual machine monitor, also known as a hypervisor. So this is one way we can run things. And then what the hypervisor or VMM provides is virtual hardware. So we've got one or more virtual hardware. And then on top of the virtual hardware, we have our guest operating system. These could be different, right? So this guest operating system might be Windows. This guest operating system might be Linux. And then on top of that, we have our applications. So we might have on top of this Vim, and let's say GDB. And this guest operating system may be running, again, a completely different operating system. And what are we running this? We're running, I don't know, Photoshop. So let's say this one's Windows, this one's Linux, and this one's Windows. And so we're running a Windows version of Photoshop here. So the abstraction that this VMM is providing is a duplicate of the underlying hardware. When I say duplicate, that's not quite the case. So it is the similar kind of hardware. So as an example, let's say the hardware here actually has, I don't know, 64 gigabytes of memory. It might not be providing virtual hardware that provides 64 gigabytes. Maybe it's actually providing 32 gigabyte. That is sharing out some of the physical memory. So it doesn't have to be an exact duplicate of the hardware. Another example might be that the underlying, well, I don't know, let's give an example. Let's say there's a Ethernet controller on this hardware. It might be providing a generic Ethernet card to this virtual hardware. The VMM knows how to receive communications for that generic Ethernet and then send it down to the appropriate specific Ethernet controller that's actually on the real hardware. So it is an idealized version of the hardware in the sense that it is sort of a standard vanilla version of the hardware often. Let's just look at the difference between these two abstractions. So if we look at the process abstraction, that'll be different from the hardware abstraction. So in the process abstraction, we have non-privileged registers and instructions. That is, the abstraction that the operating system provides for a process is you don't get to use certain instructions. As an example, on the x86, in and out instructions, for example. If we have a hardware abstraction instead, then we get access to all registers and instructions. What else? Here on our process model, we've got virtual memory. In the hardware abstraction, what do we have? Well, we actually don't see all of the real memory. So we are restricted in some cases from what memory we can see in the virtual hardware. So we still have virtual memory, but we also have the MMU, or at least we have an abstraction of MMU. So we have what looks like a really functioning MMU. There has to be some work for the VMM to make that work in conjunction with other pieces of virtual hardware, including things like managing isolation and so on. In the process abstraction, we have signals. So signals are a call from the operating system to a process that says that something's happened. In the case of the hardware abstraction, we're down to the hardware. That is, we get traps and interrupts. For process, we have file systems and sockets. For hardware abstraction, we have I/O devices and DMA, right? This DMA, again, is direct memory access, where an I/O device can directly write to memory without having the CPU as an intermediary. So these are all the things you need to write an operating system. Right? You require, in some sense, a lot more software on top of a hardware abstraction than you do on a process abstraction, because you need all of the operating system type stuff. But since that's what an operating system But since that's what an operating system expects, this is the way to run another operating system on top of some other VMM operating system.
One way you could think about virtualization is with simulation. So you can imagine you just basically, in the VMM, interpret each instruction. Right? And then what you would do is go ahead and maintain state of the virtual machine. So you maintain state for, let's say, the registers and memory. Right? Registers could just be maybe global variables. Memory could just be a big array that you've allocated. And then you'd have to emulate, let's say, I/O. This would all work. You would go ahead and get the security that it would not be accessing anything outside of this interpreter. And you would also get fidelity. But the problem is the performance would be awful. You just wouldn't have that. Because it'd take certainly probably an average of 10 to 50 instructions per interpreted instruction. So this would not be good. Now you could do something like compiling, and that might be a better idea. But think of, for instance, the Java virtual machine. Right? Initial versions of that were just an interpreter and were slow, but now they do a lot of work in terms of actually compiling the Java virtual machine opcodes into native instructions on the fly. So another possibility would be just go ahead and execute the CPU instructions directly, when possible. Okay, so what would that mean exactly? I mean, you could do, for instance, you could add EAX, EBX. Yeah, doing something like that is fine. You can push long, EBX, that's fine. You can make a call, that's fine. The problems are any privileged instructions. So if you had something like, an interrupt 48, that is an issue. Or if, let's say, you're running kernel code and you do something like turn on or off interrupt, those would also be problems. So any of those privileged ones, in, out, etc. So these you couldn't run directly, plus all other privileged instructions, because this would violate the safety requirement. Okay, because if your if your virtual machine has access to all privileged instructions, it can go ahead and just break out of whatever jail you've set it for. If you've set a page table that only allows to talk to or reference particular memory locations, it could just change that page table or change the register to refer to a new page table that allowed it to get access to any memory. So it's safe to be going ahead and doing regular unprivileged instructions, but it's not safe for all the privileged instructions. So here's the idea. The idea is something like this. We're going to go ahead, this is our real hardware, and our VMM is going to run at CPL0. And then our guest OS, right, is running on virtual hardware. This virtual hardware is all running at CPL3. It thinks that the OS is at CPL0. All right? And when it's running an application, it's at CPL3. So what would happen here is, as we're running, again, we're actually running this at CPL3. All right? And so what that means is, as we're running, this instruction works fine, this instruction works fine, a call works fine. If we try and execute an int48, what would happen is we would, let's see, this would be a case of, let's say, an application making a system call. That would cause a trap to CPL0. So that would actually go into the VMM. And the VMM would then have to go back in, figure out what the IDT is for the guest OS, figure out where to actually go, and then go in and start executing code back into the guest OS. Similarly, if we were executing in the kernel here, and we did, let's say, a set interrupt, then, so the VMM could actually have some virtual state. So if we expand this, virtual state for this guest OS. What virtual state might there be? Well, all of the privileged state. So if you look at the unprivileged state, like what's the value of EAX or EBX, that's just stored directly in the registers. But we could store in here, for instance, the E flags, one bit of which says whether interrupts are on or off. So that if the guest OS does, let's say, a clear interrupt, then what's going to happen? Clear interrupt is a privileged instruction. That's going to cause us to trap into CPL0, which is in the VMM. The VMM is going to look and say, oh, it's a CLI that's happening. Therefore, I'm not going to actually turn off CLI in the real E flags, right? I don't want my interrupts off. I need to still run it. Instead, I'm going to turn it off here in the fake E flags. These are the fake E flags that if the guest OS tries to, let's say, push the E flags onto the stack, again, we will, that's a privileged instruction, we'll break into the VMM, and what it will push is the virtual machine's idea of the E flags and not the actual E flags of the real register. So this idea is called trap and emulate. And it's historically the way that virtual machine monitors have been written. So the CLI STI, as we've said, what that would do is change the interrupt state of the E flags and probably would do nothing about changing the actual interrupt state of the hardware. The guest OS, again, is never going to see the real E flags. It's only going to see the virtual machine's idea of the E flags. These virtual E flags is what we can really think this is, virtual. Now we need to figure out what to do about memory. Okay, so we want to maintain this illusion that each VM has dedicated physical memory. So this is our guest physical mem that it sees as memory from 0 up to some mem top. All right. This memory is actually going to be allocated by the VMM, and it's not physical at all. It's a virtual address space. So this actually maps to physical memory. And each page has a mapping. And this is going to be a map maintained by the virtual machine. Sorry, the virtual machine monitor for each virtual machine. So it will contain a mapping that maps from guest physical memory to real physical memory. We can call this, let's say, host physical memory. There's another mapping that's happening though, and that mapping has to do with the guest OS. So the guest OS is maintaining actually many address spaces possibly, that is guest virtual memory. So these are virtual addresses, and here we might have a page up here that is mapping to the first page of what it thinks is physical memory that actually maps to this location in the host physical memory. So this mapping is maintained by the guest OS's CR3 register. Right. So it manipulates the page directory, page tables, and such that it gets the mapping that it wants. It has complete control over all this physical memory and assigning basically what virtual addresses map to that. Just like any OS, it may be switching CR3s. So for instance, as you switch processes, it would switch CR3s. So it might have many different address spaces for different processes, all of which go into some subset of this memory. Right. But how are we going to actually, so the problem is when we do a memory access, we cannot afford to, in terms of speed, afford to go ahead in the virtual memory monitor and have the virtual memory monitor get involved with every memory access by first looking and saying, okay, what's the guest OS's CR3? Let me go ahead and figure out what this mapping is to here, and then go ahead and let the virtual memory hardware go ahead and do this second mapping. Instead, what we're going to do is maintain a shadow page table. And this shadow page dir is going to capture basically from, so it's going to be a mapping from a guest virtual address, and coming out, we will get a host physical address. I mean, these are really pages, right? This is at the page level. So a guest virtual page number going to a host physical page number. This is what we are going to actually store in the CR3 register. So this will be the active page table. How do we fill this out? Well, we can certainly just look for every entry here in this virtual address, virtual address, every page. We can figure out what's the mapping from here to here, what's the mapping on this VMM map, and then set it in here. The only real question is, when do we do that? And the answer is, we're going to do that on any changes to this guest OS's page directory or page table. So when do we update the shadow page dir page tables? We're going to update them whenever. So if the virtual CR3 changes, then we're going to get a whole new mapping, and so we need to go refill in this shadow page directory. Or any writes to the virtual page dir or page tables, right? This CR3 points to a particular page directory. We're going to go ahead and make sure that if the guest OS does any writes to that, that we can then go ahead and capture that and update them in our shadow page table. So how do we do that? Well, we just need to make sure that these are read-only. So we're going to use the MMU to go ahead and mark the contents of the page directory and the page tables referred to by the guest OS's CR3 as read-only. And that way, if the guest OS tries to write to them, we'll go ahead and get a trap in the VMM and get notified. And then we can go ahead and update those particular entries in the shadow page directory. So that's how we can set up this mapping such that our guest OS can be running at full speed. It can be running instructions that access memory, because whenever it issues an address, it's going to be issuing a guest virtual address. It thinks that the MMU is going to be actually doing this translation, but the MMU is actually going to be doing this two-stage translation that we have pre-computed. So we're going to basically say, let's just to make this clear, that the shadow mapping goes directly from a guest virtual memory address to a host physical memory address. Not a complicated thing to figure out what it is. Just one step here and then follow it here. That'll tell you where you go. But we're going to maintain that mapping in our shadow page directory page tables. So that allows memory access at full speed. We don't need to pay any extra price to access memory, to read or write memory. All that we really have to do is make sure we're updating the shadow page table, but that's only as changes happen to the guest OS's page directory or page table. Now, one question might be, why doesn't the VMM just modify this page table in place? So as the user is trying to make a change to a particular guest physical page number in the page table entry, why can't we just update it to be the actual host physical page number? And the reason is that the page tables and page directories are readable by the guest OS. Right? It may very well want to read. We do that in JOS, for instance, as we walk page dir. It's very common for us to go walk the page directory, look at page table entry, see what the bits are, and so on, and possibly certainly see what the
physical page number is. So it's important that that not be modified.